Hello students, welcome to another lecture of number theory. In previous two lectures, we have seen the definition of divisibility and one theorem. Today, we are going to discuss the division algorithm. For the division algorithm, first of all, recall the well ordering principle. Well ordering principle. Well ordering principle. Well ordering principle states that every non-empty set of positive integers, every non-empty set of positive integers, every non-empty set of positive integers contains a least element, means every non-empty set of positive integers contains a smallest number. That is, suppose we know that the set of integers is up to -2, -1, 0, 1, 2, 3 and so on, and the set of positive integers is, we denote it as z plus, is 1, 2, 3, 4 up to so on. This statement means any subset of these positive integers contains a least element, means every non-empty subset of this z plus has a least element, means there is an element which is smallest among all the remaining elements. You all know that the difference between set of positive integers, set of negative integers is -1, -2, -3, -4 and so on. This is the set of negative integers, this is set of positive integers. 0 is not included in this either positive or negative number because of the special properties of 0. Whenever we include 0 in this set, we call this set as set of all non-negative integers. You all know about that. Now our division algorithm. Division algorithm. Division algorithm. We have to prove this result. Now theorem, that is statement of division algorithm. If a and b are any two integers, a and b are any two integers, a and b are any two integers with a is non-zero, that is a not equals to 0, then there exist unique integers, there exist unique integers, there exist unique integers, there exist unique integers q and r, small q and small r, such that b is equals to aq plus r, where 0 is less than or equals to r is strictly less than mod a, is strictly less than mod a. 0 is less equal r is, and r is less than mod a. This is the statement of our division algorithm. Here we have given two integers a and b, and a is a non-zero integer. So here is the restriction on our a is non-zero. Then there exist unique integers q and r, such that b is written in the form b is equals to aq plus r. For example, if we divide any number, suppose for example 13, so we write 13 as 4 into 3 plus 1, So if a is equals b is equals to 13, a is equals to suppose 4, then there exist unique integers, this q and this r, such that b is written in the form b is equals to aq plus r. Here q is quotient and r is remainder. When we divide any number with some another number, then we get some quotient and some remainder. This is our division algorithm. This is, for example, you don't need to write in your notes. So to prove this result, we have given a and b are integers with a is non-zero. Here a is non-zero, so a is either a positive integer or negative integer. So first of all we prove this result for positive integers, and now then we prove this for negative integers. So case first, if a is greater than 0, case first, if or a is strictly greater than 0, a is not equals to 0 and a is integer, so a must be strictly greater than 0. Now in this proof we are going to construct the set. Let us consider the set, capital S is equals to, consider the set b minus aq. This must be another integer such that this b minus aq is greater than or equals to 0. If construction is very simple, in this statement we have given that b is equal, we have to prove that b is equals to aq plus r. So what is our construction? B, this aq is taken here, so b minus aq is another integer, since this q is integer, a is integer and b is integer, so b minus aq is again integer. So this construction is very simple. S is equals to b minus aq such that this b minus aq is greater than or equals to 0. We have to prove b is equals to aq plus r, so we consider this set. Now first of all we will prove that this set is non-empty. And after that we will use the well ordering principle, and this set contains some smallest element. The smallest element we are going to say r, and after that we will prove this result. So since we have given this, we have considered a is greater than 0, since this a is greater than 0, and again a is an integer, a is greater than 0, strictly greater than 0, and a is integer, so after 0 there must be 1, so a is greater equal 1. A is strictly greater than 0, and after 0 which is the integer is 1, so a is greater must be greater equal 1. Since a is greater than 0, this implies yes, a is greater than or equals to 1. Multiplying both side by mod b, we get mod b into a is greater than equals to mod b into 1, that is mod b. This is from multiplying by mod b to get this result. This implies now adding plus b on both sides, we get b plus mod b into a is greater than or equals to b plus mod b, since adding mod b on both sides. So this is again greater than or equals to 0. This is again greater than or equals to 0, since our a is greater than or equals to 1, and we multiplying by mod b. Mod b is again a positive integers. Here we have not given b is either negative or positive or any condition on b is any integer, but if b is positive integer then mod b is again positive. If b is negative integer then mod of negative number is again positive, so mod b is positive. A is greater or equal 0, so their multiplication is again positive. Mod b is positive, so b plus mod b is again greater than or equals to 0. If b is negative, then this minus number plus mod of that b is going to positive. For example, if b is equals to suppose minus 2, then mod b is equals to 2, so their addition minus 2 plus 2 is going to 0, so this b plus mod b is greater than or equals to 0. If b is negative, then b plus mod b is equals to 0. If b is positive, suppose b is equals to 3, then 3 plus 3, that is b mod b is equals to 3, so 3 plus 3 is equals to 6, which is greater than 0. Then b plus mod b is going to greater than or equals to 0, is greater than or equals to 0. This implies, it is a rough work, this implies b plus mod b times a is greater than or equals to 0. Here b plus mod b times a is greater than equals to this b plus mod b, and b plus mod b is greater than equals to 0. So this our b plus mod b times a is greater than equals to 0. b plus mod b into a is greater than or equals to 0. So we simplify this as b minus of mod b into a. Minus minus gets plus, so b plus mod b times a, we write it as b minus of minus b minus mod b into a, which is greater or equals to 0. Just simplified this plus sign into minus 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 gets plus. So b, this looks like b minus a q, this looks like b minus a q. So this element must belongs to our set. Yes, b minus aq is an integer and b minus aq is greater than or equals to 0. Here b minus aq, this number looks like b minus aq, and this again greater than or equals to 0. So this number goes in our set yes. This implies b minus mod b times a belongs to our set yes, belongs to our set. So this implies in our set yes there is some number which is b minus a q, b minus minus b times a. So this number belongs to set of our set yes, implies set yes is non-empty, yes is non-empty, this is non-empty subset of, this yes is non-empty subset of whatever our well ordering principle says that every non-empty subset, that is every non-empty set of positive integers contains a least element. So our this set yes, that is b minus aq set is non-empty and which is subset of positive integers, or we can say that the subset of set of natural numbers union singleton 0, set of natural numbers union singleton 0. This is nothing but the set of positive integers. Therefore, or you can write this is non-empty subset of positive integers. Therefore, by well ordering principle, by well ordering principle, therefore by well ordering principle yes has least element, yes has least element, or well ordering principle says that every non-empty subset of positive integer contains a least element. There here the set yes is non-empty and which is subset of positive integers, so yes has least element. Suppose we say that element as say r, small r, thus our r is in set yes and r is smallest among the all remaining numbers in that set, that is r is less than or equals to y for all y belongs to yes. Yes is least element of our set yes, so r is least element among all the remaining elements, so r is less than or equals to y for all y belongs to yes. Since r is least element, so all the remaining element must be greater than or equals to r, so r is less than or equals to y for all y belongs to yes. But r is in yes, this is the least element of our subset, our set yes, but R is in that set yes. So elements in the set yes are in the form of B minus AQ. So R must be in the form of B minus AQ. Yes. So R is equals to B minus AQ for some Q belongs to Z. For some Q belongs to Z, that is Q may be any integer. Therefore, we simplify it as B is equals to AQ plus R. After sending this AQ here, we get R plus AQ, that is AQ plus R. B is equals to AQ plus R, and R is greater than or equals to 0. Since R belongs to S, R is the member of our set yes, and the all elements in this set yes are greater than or equals to 0. So our R is again greater than or equals to 0. Now it's remain to prove that for the case A, that is for A is positive, it's remain to prove that R is less than mod A. Now it's remain to prove that R is less than mod A. Here A is, we have taken A is positive, so mod A is again positive, or that is we have to prove R is less than A. A is positive, so mod A and A are same. This proof we will prove by contradiction. This proof by contradiction. It's proved by contradiction. If possible, suppose we are going to assume contrary as R is greater than or equals to A. On contrary, suppose R is greater than or equals to A. This implies R minus A. R minus A is greater than or equals to 0. This element R minus A is greater than or equals to 0. This element is again looking like B minus A into Q. Suppose Q is equals to 1, then B minus AQ, and also greater than or equals to 0. So this element is looking like this B minus AQ, such that this B minus AQ greater or equal to 0. So therefore this element R minus AQ belongs to, R minus A belongs to set of, our set of yes, R minus A belongs to yes, but this R minus A, we are subtracting some another integer from R minus A is strictly less than R. Is it clear? R minus A, R is integer and A is again integer, and we are subtracting this R, we are subtracting this A from R. So R minus A is less than R, and our R is least element of yes. Yes, as least element say R is least element of yes, and R is least element of yes. R is least element of our yes set. Yes is equals to B minus AQ. Here B R minus A is again in the form B minus AQ, which is greater or equal 0. So R minus A must belongs to yes. So R minus A is less than R, but R is least element. So we get the contradiction, which is contradiction. R minus A is less than R, and this R minus A belongs to set yes. This implies this is contradiction to our R is least element of yes, which is contradiction. Equation 2, R is least element, R is least element of yes. Therefore R must be less than A. R must be less than A, that is R must be less than mod A. We are writing R is less than A, that is R is less than mod A, since A is positive. So their mod a is again a positive number. Therefore for integers a and b, there exist integers q and r such that b is equals to a q plus r, where this 0 is less than or equals to r is less than a or mod a. This is for the case first. This proof is for the case first, that is a greater than 0. Now we have to prove this result for a is less than 0. Now case second, if a is less than 0, here for a is strictly greater than 0, and now we are going to prove this for a is strictly less than 0. Since we have given a is non-zero, then either a is positive integer or a negative integer. For first of all, for positive integers we have proved this result. Now we are going to prove this result for negative integers. Okay, second, a is less than 0. Our a is less than 0, so a is in the form of -1, -2, -3 or so on, any integers in between them. So if a is less than 0, then mod a is greater than 0. For any negative number, if you take the modulus or absolute value of that number, then it is positive. So mod a is greater than 0. Now this is looking like a greater than 0. So replacing a by mod a in this case, we get our result. Now replacing a by mod a in above case or case first, we get just a second. We get b is equals to mod a into q. We are replacing a by mod a, so b is equals to a q plus r is become b is equals to mod a q plus r, where 0 is less than or equals to r is strictly less than mod a, replaced a by mod a. So we can write it as b is equals to minus a into q prime plus r. Here a is negative number, and we have taken the modulus of negative number, and also we know that the definition of absolute number or modulus in T.Y.B.Sc as mod a. For mod a there are three values, 0, a and minus a. 0 and minus a. For if a is equals to 0, then mod of 0 is 0. If a is positive number, then mod of that positive number is, suppose a, then mod of a is equals to a. If a is negative number itself, then we write mod of a is equals to minus a. So replacing a by minus a, we get this. So we can write it as a into minus of q prime, multiplying minus sign here, plus r. Here this as it is, where 0 is less equal, r is less than mod a, again where this 0 is less equal, r is less than mod a. Just making some simplifications here, which is equals to a into some q plus r, this is r, where q is equals to minus of q prime and 0 less equal, r less than mod a. So our result is proof for the minus of a. In this case, also for any two integers, a and b, also for any two integers a and b, there exist q and r such that b is equals to a cube plus r, where 0 is less than or equals to r is less than mod a. In second case, for a is less than 0, in second case for a is less than 0, we take modulus of that negative number, so mod a is positive. Now for positive integer, a is negative integer, so mod a is going to be positive integer. So this positive integer, we approve this result. For positive integers, we make this some construction and prove this result. B is equals to a cube plus r. Here mod a is positive, so we can apply this case here. So replacing a by mod a, here we get b is equals to mod of a cube plus r. Replacing a in this equation, we get b is equals to mod a cube plus r, where 0 is less than or equals to r is less than mod a as it is. B is equals to mod a cube plus r, where 0 less than r is less than, this is as it is. Now here a is negative number, so that's mod a is positive. Taking modulus of negative number, we have the definition. Of absolute value. Just a second. We know the definition of absolute value. Absolute value. We have seen this in T.Y.B.Sc. Definition of absolute value says mod of any integer is either equals to 0 or a or minus a. This 0 whenever a is equals to 0, if a is greater than 0, and this if a is less than 0. If a is less than 0, then mod of that negative number becomes minus a. That is, these two cases are simple. For the third case, if suppose, for example, if a is equals to minus 3, that is a negative number. For a is equals to minus 3, mod of a, which is equals to mod of minus 3, we take is 3. Is 3, this 3 is taken from this third case, that is minus of minus a, that minus a is minus 3. Minus of minus a is equals to 3. So we get 3. Mod of minus 3 is equals to 3 as minus of minus 3. Negative of negative number becomes positive. This is the definition. Here we use that mod of a is equals to minus a. For negative number, we have taken this mod positive, and this for this positive number we use the case first. B is equals to mod a cube plus r. So taking mod for negative number, we get mod of minus a is equals to a. So we use that definition here. B is equals to minus of a. This minus a because of the definition of absolute value. Mod of a is equals to minus a whenever our a is less than 0, or case second is a is less than 0. Therefore, for negative numbers, mod a is equals to minus a. B is equals to minus a times q prime plus r. So just simplifying this, that is, for b is equals to multiplying minus to this q prime, we get a into q prime minus of q prime plus r. So taking this must be another integer, so a q plus r, taking minus q prime as q. So we get the required result, b is equals to a q plus r, where q is equals to minus q prime. And this is the proof of our division algorithm.